The American Museum of Natural History and NASA present Field Trip to the Moon.
We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
Nearly 40 years ago, humanity set foot on the moon. Apollo 11, 1969. Landing on the moon. Neil Armstrong's 1969 moonwalk. Soon, we will return. Upcoming Orion mission. Your journey begins now. Field trip to the moon. Introduction is selected. Feature presentation.
Spacecraft now to full internal cooling. The cooling load has been shared with the ground cooling. T-minus 90 seconds and counting. T-minus 90 seconds and counting. At T-minus 1 minute 15 seconds, the spacecraft, as we move down through the count at the T-minus 17 second mark.
Welcome. You are about to embark on a voyage to the Earth's moon. Only a few astronauts have ever actually taken this trip, and it usually lasts 3 days. But through state-of-the-art visualization technology, we will complete our journey in just a matter of minutes. As we arrive at Kennedy Space Center's Vehicle Assembly Building, let's take a look at one of the 2 Ares rockets NASA plans to use in their upcoming mission to return to the moon. The 2 rockets, called Ares 1 and Ares 5, will carry everything we need for our mission. Us, our spacecraft, our life support supplies, and our lunar lander.
Cooling load has been shared with the ground cooling. T-minus 90 seconds and counting. T-minus 90 seconds and counting. At T-minus 1 minute 15 seconds, the spacecraft batteries will be turned on for launch.
This is the Ares 5 rocket. It can carry nearly 100,000 pounds to the moon. That's as heavy as 4 school buses. The entire assembly stands more than 360 feet tall. The long tubes you see on either side of Ares 5 are reusable solid rocket boosters, the same boosters that are used on the space shuttle. but the Ares 5 central core more closely resembles the Saturn V rockets that carried the Apollo astronauts to the moon in the 1960s and 70s. We need a rocket large and powerful enough to escape Earth's gravity and to navigate our way to the moon, nearly 250,000 miles away from Earth. With a rocket like this, we are ready for our trip to the moon.
17, guidance release, 15, 14, 13, 12, 11, 10, 9. We have ignition sequence start. The engine's now building up to 7.7 million pounds of thrust. And we have a liftoff. Turn on, moving back.
As we leave Earth, we can clearly see the bright haze from the atmosphere, the protective layer of air that surrounds our planet. This amazingly thin layer contains the oxygen and nitrogen that we breathe, plus the carbon dioxide that fuels the plants. The atmosphere also contains clouds, storms, rain, snow, and just about any kind of weather that you can think of. Our flight path will take us one full orbit around Earth before we are able to change our trajectory for the moon. We're heading east, and below is the Atlantic Ocean, which contains the Earth's most precious resource, water. Nearly 3/4 of the Earth's surface is covered with water. Even though the Earth is covered with water, only 1% of it is fresh water that we can drink. And since we know that all living things need water to survive, well, that makes water one very important resource on our planet. We're approaching the western coast of Africa and the vast expanse of the Sahara Desert. The Sahara is as large as the United States. Not much water here, but watch as the dry Sahara gives way to the rich green jungle of the Congo. And as we pass the western border of Tanzania, if you look south, you can get a glimpse of some of that rare fresh water in the giant lakes that outline its border. We are flying over Madagascar now and approaching the day-night boundary. What is the day-night boundary? Well, it takes the Earth exactly 1 day or 24 hours to rotate on its axis. This rotation carries the planet from daylight into darkness and back again. And we can see this day-night boundary line from space. Underneath us is the immense darkness of the Indian Ocean, virtually uninterrupted by islands or civilization. But as we approach Australia, you can see its western coastline dotted with lights. And where are these lights coming from? Cities. And where there are cities, there are people, lots of people. Even from space, the signs of life on Earth are visible. We are now traveling over Earth's largest ocean, the Pacific. You may notice the clouds below appear to be illuminated. And what's lighting up the clouds? The sun, of course. Light from the sun gets reflected off the moon, which in turn illuminates the clouds. We can also see our own Milky Way galaxy arcing through the nighttime sky. Though it looks like a band of white light, this Milky Way galaxy contains billions of stars, many like our sun. A gorgeous sunrise greets us as we move from darkness into light. A sunrise from orbit, the kind of sunrise most people will never see. We're now crossing the Gulf of Mexico, on our way to the place where we started our journey, Cape Kennedy. There's Florida's Panhandle in front of us, and it's time to leave Earth orbit and follow our trajectory toward the moon. A trajectory is a path or a course created to get from one place to another. Plotting that course through space is a bit tricky since everything in space is moving. Not only do we have to figure out how to get to the moon, but we have to determine where the moon will be when we arrive, not only in its orbit, but also in its rotation. We will need to fire our engines again, just as we did taking off from Earth. The amount of energy we need to push us out of low Earth orbit onto our path to the moon is small compared to the energy that it took to get us into orbit. We can see the moon rising ahead of us now, and it's time to fire our engines. We are now on our way to the moon. Let's use our spacecraft's technology to take a look at a few things that we wouldn't normally see out the window of an actual ship on its way to the moon. For example, notice the positions of human-made satellites around Earth. Those in high orbits are often used for communication. Anyone ever heard of GPS? Well, these are the satellites that enable us to locate and communicate with people all over the world. The satellites in lower orbits, closer to Earth, are often used for things like monitoring the weather. In the last 50 years, we've put a lot of stuff into orbit around the Earth, and these devices have become an important part of our daily lives. Let's step outside and take a look at our own spacecraft. Here is our craft. While it continues its journey to the moon, we can take some time to explore the environment in space around Earth. Most people think of space as being totally empty, but the space between the sun and the planets, even between the Earth and the moon, actually contains many tiny particles that we can't see. Most of these particles come from the sun. They fly through space so quickly that if a burst of them were to hit a satellite, a spacecraft, or especially an astronaut,
it made sense to send robotic pathfinders then, and it makes sense to do so again as we prepare to send astronauts back to the moon. There is much that we know about the moon, but there is more that we must learn before we return, this time to set up outposts. That's where the Lunar Precursor Robotic Program comes in, leading the way back to the moon.
Hi, I'm Tony Lavoie with NASA's Lunar Precursor Robotic Program. Our journey back to the moon starts here. I would like to take you on an important upcoming mission that will tell us more about the moon than we've ever known before. Allow me to introduce the major players. First, the Lunar Reconnaissance Orbiter, or LRO, will help inform us about the moon and give us critical knowledge needed to help design and plan for sustained human return to the moon. From this lunar orbiting satellite, LRO will generate a comprehensive atlas of the moon's topography and resources. It's also going to tell us a lot about day-night temperatures and lighting conditions, both of which are critical to know for an outpost. LRO is being developed by NASA's Goddard Space Flight Center. Launching with LRO is the Lunar Crater Observation and Sensing Satellite, or LCROSS. Its main job is to look for the presence or absence of water ice in a permanently shadowed crater at the moon's south pole. Water ice is valuable because it can be relatively easily processed into many things needed for life on an outpost, including water, breathable oxygen, and even rocket fuel. LCROSS is a low-cost, fast-paced project from NASA's Ames Research Center and Northrop Grumman. Now, imagine it is late 2008. We are at Cape Canaveral, and our Atlas V launches our pathfinding mission skyward. We build up speed as we roar through and out of the atmosphere. Everything checks out, and the Atlas upper stage boosts LRO and LCROSS toward our closest celestial neighbor. The trip takes about 4 days. As we approach, LRO separates. This is where it and the L-Cross with the upper stage go their separate ways. LRO works its way into a low circular polar orbit, the lowest lunar orbit ever. It will only be 50 kilometers or a little more than 30 miles above the surface. This is a great vantage point for its year-long fact-finding mission. It will map the moon with high-resolution imagery as well as a host of other data collection instruments. As LRO starts its mission, L-Cross and the spent upper stage get a speed-building running start for what will be an exciting impact on the moon. They slingshot around the Earth a couple of times, then hurtle toward the lunar surface. Just a few hours prior to impact, the combined upper stage and L-Cross separate so that the L-Cross spacecraft can watch the upper stage impact. With L-Cross instruments watching, the Atlas upper stage will impact a permanently shadowed crater on the moon, where we might expect to find water ice. This impact kicks up a major dust cloud or ejecta field. L-Cross analyzes that moon cloud, telling us what the crater's surface is made up of, and hopefully what can be farmed later to support outpost activity. After that impact, the L-Cross spacecraft then hits the moon as well, with a smaller impact because of its smaller size, but still visible from Earth-based telescopes and possibly LRO to look at the ejecta cloud. Meanwhile, LRO continues its mission of discovery. This is an exciting and ambitious mission. It will generate volumes of data that we will closely analyze. That new knowledge will make future human exploration safer and more efficient. These are exciting times, and I invite you to follow our progress on this mission of exploration as we lead the way back to the moon.
Lunar Precursor Robotic Lunar Reconnaissance
Listen, Tranquility Base here. The Eagle has landed. Roger.
When I was a little girl and people were always asking me, what do you want to be when you grow up? And I used to always go, I want to work up there. As an engineer, you dream of a job like this where you get to follow in the footsteps of some of your childhood heroes. And of course, for me, the Apollo missions, seeing these folks on TV step on the moon and work for NASA, as an engineer, it's just a dream to be able to say, you know, I want to do that too, and here I am. Hi, I'm Kathy Petty, and I've got the coolest job at NASA. I get to work on a project called the Lunar Reconnaissance Orbiter Project, or LRO. We're going back to the moon. And guess what we're doing right now? We're building all the parts of the spacecraft at Goddard Space Flight Center in Maryland. The LRO instrument suite is comprised of 6 instruments and 1 technology demonstrator. And they are geared towards providing us a variety of data sets ranging from a thermal map of the moon, global topography, and most importantly, looking for resources like water ice on the moon. The entire suite should provide more of an atlas as opposed to a map, so that we know where to go on the moon, where to have the safe landing sites, and where to put things like lunar outposts in the hopes of having human exploration in the near future. All of our instruments have been built, so right now they're all being qualified. Our propulsion tanks, all the fuel that's going to take us to the moon and get us into the orbit, already done, completed. So we're in the throes of the assembly sequence. All the engineers and technicians and all of our business folks are working very hard to make sure that we successfully integrate it and test it and get ready for our launch next year. If I were to dream, I would love to see that LRO lived way beyond, decades beyond its supposed life, and was able to do more than what we said it would do, and maybe discover something that would not only enable human exploration, but do something that just made it happen like a lot quicker. Or we look back on the Earth and we were able to help life here on Earth because of something that we never even thought of because of the little project called LRO. That would be great. That would be awesome.
Lunar Reconnaissance Orbiter is selected. Lunar Crater Observation.
I was strolling on the moon one day in the merry, merry month of December. May.
More than 35 years have passed since humans last walked on the moon. NASA's current mission is to once again take a giant leap for mankind by establishing a human outpost on the moon. To pave the way, robotic missions surveying the moon will launch in late 2008.
The Lunar Reconnaissance Orbiter, or LRO, and the Lunar Crater Observation and Sensing Satellite, or LCROSS, will launch together on an Atlas V rocket.
Their mission is to provide critical information to NASA as it plans our future on the moon.
We here at NASA Ames Research Center are extremely excited to be designing and conducting the LCROSS mission. The goal is to determine if water, perhaps in the form of ice or hydrated minerals, exists inside a permanently shadowed crater on the south pole of the moon.
Water is an extremely valuable and versatile resource. Water can be split into hydrogen for rocket fuel and oxygen for breathing. It can be mixed with moon dust to make concrete used in building shelters. It also makes an excellent shield to protect against radiation. Since any ice on the moon might be buried underneath a layer of rock and dust, we need some method of getting the ice out into the open and detecting it.
The LCROSS mission accomplishes this with 2 space vehicles. The Centaur upper stage of our moon rocket will be used as a 2,200 kilogram kinetic impactor, excavating a crater approximately 20 meters wide and almost 3 meters deep. More than 250 metric tons of lunar dust will be lofted above the surface of the moon.
The shepherding spacecraft, built by our partner Northrop Grumman, guides the Centaur upper stage to the target. It also carries cameras, spectrometers, and a photometer to analyze the debris plume to look for the presence of water vapor, ice, hydrocarbons, and hydrogen, which is one of the components of water.
The science instruments on board the LCROSS spacecraft cover an extremely wide spectrum. We have spectrometers that can see organics, hydrocarbons, and byproducts of water ice. We also have infrared cameras that can see hydrated minerals, water ice, and water vapor. In addition to telling us if water exists on the moon, the science that comes out of this data will be used for many years beyond the LCROSS mission.
3, 2, 1, 0, and liftoff.
2 hours after launch, LRO will separate from LCROSS and continue on its way to the moon. 5 days after launch, LCROSS and the attached Centaur will execute a flyby of the moon. They will then enter into several large looping orbits around the Earth for the next few months of the mission. We will use this time to check instrument calibration and refine our trajectory for lunar impact.
About 7 hours before the impact, the shepherding spacecraft will separate from the Centaur and position itself to observe the impact at the south pole of the moon. For the next 4 minutes after the impact of the Centaur, we will receive real-time data as the shepherding spacecraft flies through the plume and scans the ejecta for signs of water.
The shepherding spacecraft will then impact the moon, creating a second plume of lunar dust.
Both impacts will be closely observed by professional astronomers on the Earth, using some of the world's greatest observatories. We also believe there is a chance that the impact plume may be visible in 10 to 12-inch telescopes. We are encouraging both professional and backyard astronomers to participate and contribute their observations to this exciting mission.
We are at a key point in human history. Humanity is preparing for its next stage in our development, and that stage is settling the solar system.
As NASA moves forward with our exploration programs, one of the most important things we need to figure out is how people can live for long periods and eventually permanently off the Earth.
If we can identify water ice at the poles of the moon, we can use that water to live off the land.
We are excited, proud, and honored that the LCROSS mission has been chosen to be a first step on our long journey as humanity takes our next giant leap back to the moon, to Mars, and beyond.
Lunar crater observation.
Extras is
Our moon. The moon looks peaceful in Earth's sky. But its story has a violent beginning. 4.5 billion years ago, the planets of our solar system were still forming. The young proto-Earth glowed at more than 3,000 degrees Fahrenheit. An object the size of Mars occupied an orbit close to Earth's. Making collision inevitable. The collision sprayed molten rock into orbit around Earth. As the rock cooled, it formed larger and larger clumps. Until the moon took shape just 1 month later. The moon formed a mere 14,000 miles from Earth. But its orbit has been widening ever since. The moon now lies 240,000 miles away. Evidence of the moon's violent formation comes from analyzing its composition. Dark regions show rock that formed quickly after the heat of impact. Light regions formed later and are rich in iron. Future missions to the moon promise to deepen our understanding of its composition and evolution. American Museum of Natural History and NASA present Field Trip to the Moon. Are you ready for a quiz? How many humans have walked on the moon? A, none. B, 2. C, a dozen. D, 100. The correct answer is C, a dozen. 12 humans have walked on the moon. How cold can it get on the surface of the moon? A, 32 degrees Fahrenheit. B, 0 degrees Fahrenheit. C, negative 150 degrees Fahrenheit. D, negative 250 degrees Fahrenheit. The correct answer is D, negative 250 degrees Fahrenheit. How hot can it get on the surface of the moon? A, negative 100 degrees Fahrenheit. B, 32 degrees Fahrenheit. C, 100 degrees Fahrenheit. D, 250 degrees Fahrenheit. The correct answer is D, 250 degrees Fahrenheit. What did scientists discover at the moon's south pole? A. An obelisk. B. Evidence for water ice. C. Molten lava flows. D. Plant life. The correct answer is B. Evidence for water ice. What makes it possible to see the moon from Earth? A. The moon's surface gives off light. B. The moon is full. C. The moon is phosphorescent. D. The moon's surface reflects sunlight. The correct answer is D. The moon's surface reflects sunlight. Which object is closest to Earth? A. The Sun. B. The Moon. C. Venus. D. Mars. The correct answer is B. The Moon is closest to the Earth. What is the moon responsible for on Earth? A. Volcanoes. B. Weather. C. Tides. D. Earthquakes. The correct answer is C. Tides. The final question. What does a 90-pound student weigh on the moon? A. Nothing. B. 15 pounds. C. 90 pounds. D. 120 pounds. The correct answer is B. 15 pounds. A student would weigh 1/6 what he would weigh on Earth.